My name is Patrick, and today we are going to be talking about the shortest path problem and strategies to solve it. Now, the shortest path problem is essentially just how to calculate the shortest way to get from one place to another. Now, the problem requires a graph as input, and we have a graph here. The circles, or nodes, represent locations. They could be locations in the physical world or theoretical locations. And the lines connecting these nodes are called edges. If you notice here, each edge has a number by it. That number is called the edge's weight. And you can think about it as sort of like a representation of how expensive it is to cross that edge. So if we were talking about this graph in the context of the actual world, you could think of these as roads connecting different locations and the numbers representing how long it took to drive on that particular road from place S to place A. So, say you were trying to go from your house to school in the quickest amount of possible time. Turns out that if this were a graph that was accurately representing the road network where you live, the shortest, quickest path would be to go from S to B to E to G, and then finally to T. So if you look at the summation of those numbers on the roads that we actually went on, it totals up to 16. So you can think of that like the fastest you could possibly get from your house to school would be 16 minutes. What we're talking about today is different strategies to actually calculate this information and why some strategies are better than others. Hope you enjoy.
Hi, I'm Alex, and I'm going to talk about Dijkstra's algorithm. Dijkstra's is a pretty well-known shortest path algorithm, and it's well-known because it's relatively quick to implement and quick to solve the problem. So Dijkstra's takes no pre-processing time up front, so you can run it immediately, and it works relatively quickly still. Dijkstra's takes advantage of something called a priority queue. Now, a priority queue is just a queue that you can sort with whatever you want. So we've decided to sort it with the distance to that node so far. So say we're going from node S to node T. We know that it starts with a distance of 0 to S because that's where you're starting. And we want to find the distance to T. So we initialize our priority queue with S of 0 there. Now these blue things next to every node are the distance that we know you can get to that node from for sure. And because we've started just at S, we don't know for sure that you can get to any other node. So we've initialized everything to infinity. Once we find the shortest distance to T, that's what we're looking for, and that's when we finish. So now I'm going to walk you through Dijkstra's. So the way Dijkstra's works is it will pop what is off the front of the queue, so in this case S of 0, and it will look at every edge from S and make sure that the distance to that node is shorter than the shortest distance that we've already computed. So for instance, S to A has a distance of 4, which is obviously shorter than infinity. So now we update that, and we add A of 4 to the queue. Now we do the same thing for B and C. And now our queue at the end of this has A of 4, B of 5, and C of 7 in it. So now, like last time, we'll pop what was on the front of the queue. So A of 4, so we'll go there. And we'll add this edge to D with a total distance of 13. Because we got to here in 4, plus this 9 here is 13. Now B of 5 is at the front of the queue because we popped A of 4. We'll do the same thing as before. This will give us a distance of 8 to E. Now it's important to note that because this is a priority queue, even though we just added this E of 8, since we're sorting by distance and shortest distance, it will go before the d of 13 that we added earlier. So now we'll go to C. And now it's important to note that we don't add this edge here because 7 plus 4, 11, is not less than 8. So this path to E is not shorter than the shortest path that we've already computed. So we won't add this, but we will add from C to F, distance of 13. Now I'm going to step through the rest of this, and hopefully you guys get a cool time-lapse effect while it happens. Okay, so now how do we know when to stop Dijkstra's algorithm? Well, Dijkstra's algorithm stops when your destination is what you've popped from the queue. This is because you know that it is the shortest thing that's left. So there's no way you could possibly have a shorter path to it because it's the shortest path that's left on the queue. So as soon as you pop t from the queue, you know that you found your shortest path. So we pop t of 16 from the queue, we do this, and we find that this is our shortest path. S to B to E to G to T. That's how Dijkstra's works.
Hey, I'm Aditya, and now we're going to be examining A-star search, which is another algorithm that can be used for finding the shortest path. As we saw in Dijkstra's algorithm, a structure like a priority queue is oftentimes used in shortest path algorithms to decide what order the nodes are going to be visited in. And A-star search also uses a priority queue, but it orders the nodes in a slightly different manner than Dijkstra's does. So in Dijkstra's algorithm, we saw the priority queue was ordered based on how far away a node was from our starting point S. But with A-star search, we're actually going to order the nodes based on something called a heuristic value, which is going to be a guess from as to how far away we are from a node to our goal state. So A would have a guess as to how far away we are from T, B would have a guess, and C, and so on. And we're going to be looking at a particular algorithm called ALT, which uses these guesses in order to conduct an A-star search.
1, 2, 3, my baby don't mess around because she loves me so.
So the ALT algorithm takes advantage of something called the triangle inequality, which tells you that when given a triangle as such, the lengths ST plus SL is going to be greater than or equal to the length TL. And that can be rewritten as ST is greater than or equal to TL minus SL. And so this is going to give you, we're going to take advantage of this inequality to give us an estimate from S to T, for the length of S to T throughout our algorithm. And the better that this guess is, or this estimate is, the faster our algorithm will run.
Saturday morning, jumped out of bed and put on my best suit.
So in the ALT algorithm, the letters ALT stand for A-star landmark triangle inequality, as it uses all three of those components during its search. So in the ALT algorithm, we're going to pick a set of landmarks. But for the purposes of this demonstration, let's just pick one landmark. And let's let it be E, since it's kind of in the middle and evenly distributed throughout the nodes, which is what you want of your landmarks during this search. So over here, let's just write landmarks, and we're just going to have one, and it's going to be E. And then we're going to go and compute the distance from E to every other node in the graph. So we're going to have A is a distance of 21 from E, B is a distance of 3 from E, and we'll probably just speed this up, but I'm going to quickly do this now.
I've never seen a diamond in the flesh. I
cut my teeth on.
So now that we have all of our distances from E, we're going to go ahead and calculate each node's heuristic value. So the heuristic value is calculated by taking every node's distance from E and subtracting the goal state's distance from E, and taking the absolute value of that. So for A, it'd be 21, because A's distance, from A's distance to E, and then 8 for T's distance from E, so the heuristic value will be 13. And then B's will be 8 minus 3, or 3 minus 8, and we take the absolute value, so it will be 5. And C's will be 8 minus 4. And so now we're again just going to speed this up, and I'll fill out the rest of the heuristic values. So now that we have these heuristic values calculated, let's move into the actual algorithm. So as we expand from S, we see we have nodes A, B, and C. We're going to add them to our queue. And they're going to be ordered in this manner. So we're going to take each node's heuristic value, so for A it'll be 13, and also the node's distance from S, and add those together. So for A, that value will be 17. For B, that value will be 10. And for C, that value will be 11. And we're going to order such that the node with the lowest value is first in the queue. So we'll have B of 10, C of 11, and A of 17. And then we're going to pop B off the queue and examine and put node E onto the queue. And E's value is going to be its heuristic 8 plus its distance from S, which is also 8, so it's going to be value of 16. So our queue will now look like C11, E16, A17. And so the edges we've examined so far are S to B. And now we're going to pop C off the queue, and now we have nodes E and F that could potentially be added. We already have E on the queue, and its heuristic value is 8, and its distance in this direction is 11, so that's not going to be better than the value we have in the queue right now. So we're not going to modify that, but we are going to add F to the queue, and its value will be 6, its heuristic, plus 13, so 19. And so our queue will now look like E16, A17, and F19. And we have now examined S to C. And so now we're going to pop E off the queue, and we have nodes F and G to potentially be modified or added to the queue. So F has a heuristic value of 6, and its distance from S in this direction is 10. So its total value is 16. G has a heuristic value of 3 and a distance from S of 13. So G's total value is also 16 here. And so when we add them, we'll just break the tie using alphabetical order. So we'll say it's F16, G16, and A17. We now pop F off the queue. F examines T. T is going to have a value of 0 plus its distance from S of 15, 22. So it's going to be, the queue will look like G16, A17, and T22. We now pop G off the queue. Sorry, so we've examined this. No. We've examined this edge, and we've examined this edge. Okay, now we're going to pop G off the queue, and G lets us examine t again. And this time t's value is going to be a heuristic 0 plus its distance from s, which is 16 in this case. And so we're going to update t's total value in the queue, and it's now going to be t of 16, a of 17. We will, and then this edge will be examined, and then we'll pop t off the queue, at which point we would have found the shortest path from s to t in this manner.
So now that we've discussed a few of the algorithms and how they work, I'm going to talk about one of the main speedups that's commonly done. So with all the algorithms that we've done so far, we've searched from start to destination with everything. But as you can imagine, sometimes it's faster to go from both directions, from start to destination and from destination to start. This is known as a bidirectional search. So what this can offer is, if you think of how Dijkstras works, Dijkstras is expanding just the shortest distance regardless of direction. So it's kind of growing in a circle, right? Where the radius is the distance that you've seen. So it will have, on its whole search, it'll expand everything in a circle of radians from start to destination. Now, if you take that in both directions, from the destination to the start and from the start to the destination, what you've effectively done is you've created two circles, but you've cut the radius in half on each of them. And since the area of a circle is pi r squared, you are cutting the search space in half effectively, because you're squaring half twice, and thus it adds up to half the search space. So I'm going to go over how bidirectional search would work on our example. I'm going to do bidirectional Dijkstras. So the way it'll work is you'll start from the source to the destination, while at the same time starting one from the destination to the source. And it'll work the same way, where you'll keep a priority queue on each of them. So all these green arcs here are the edges that were explored in a one-directional Dijkstras. And you'll see that with bidirectional we do cut that down. So at every iteration it'll look for which queue has a shorter distance in it. So at the beginning, the destination to source queue has a distance of 3, so it'll expand that node. And then it'll add 5, so a distance of 8. But then it will expand this, because the 4 is shorter. And then it will expand the 5. And then it will expand the 7. And now the 8 is the shortest thing left in the queue. So now we'll expand this 8. And again, we get this 8 because the distance is 3 plus 5. Add up to 8. And now there's an 8 in this queue. And we do that. And then as soon as we've done this, we now have a node that's been visited from both destination to source and source to destination. And as soon as you have a node that's been visited by both, you know that you have found a shortest path somewhere in your queue. So at this point you stop the algorithm and you just go through all the possible paths that you have left in your queue, but don't add any more, and find the shortest path. So for this, it does happen to be 8 as the, or 16 as the shortest path going through this E. And as you can see, we've cut down the number of edges that we've evaluated. In this example, we only cut it down by these two, but as you can imagine, with a very large search space, you can cut it down very significantly, and it can offer great speed up. So that's how bidirectional search works. So one final part of the algorithm that we're going to talk about is something called reach. Now, the purpose of reach is to prune away as many nodes that we know aren't going to be useful as possible. So the way reach does that is by computing the reach from every node as to how far it can go and still be part of the shortest path of something. And you know that if you're farther than that, that node's not useful. So a way to think about this is, say you're driving between two major cities, like you're driving from Detroit to Cleveland. You know that you're not going to find your shortest path on some little side street in Ann Arbor. You're going to want to stick to the major roads for your shortest path. And reach effectively tries to do this because the reach of these smaller streets, or these side streets, is going to be relatively low, whereas the reach of major highways will be high. So you won't prune away the highways, but you will prune away the smaller streets because you know that they're not going to be part of any shortest path. So I'm going to give you a quick example of how reach could be computed on this graph. I'm going to compute the reach of the node E. Now, in implementation, you would compute the reach of all these nodes so that you could figure out which ones to prune. Now, the way reach works is you'll take the shorter side of the distance of a shortest path. So, say you're going from S to F, and you know that the shortest path is among these nodes, S to B to E to F, giving you a shortest path distance of 10. Now, the shorter of the two is either E to F or S to E. Now you know S to E is 8 and E to F is 2, so the shorter of the two is obviously 2. Now say you wanted the shortest path from C to T. The shorter of these two would be 8 or 4, so it's 4. And now say you wanted the shortest path from S to T, and you know that E is still on that, and this is 8 or 8. So you'll take the shorter of the two, in this case 8, and you'll do this for every possible path, every possible shortest path that E is on. So anytime E is on a shortest path between two nodes, you'll take the shorter of the two distances. Then you'll take the maximum of all of these. So you'll take the maximum of the 2, 4, 8, and whatever else is on there. So for this case, it's 8. And that gives you the reach of E. So E has a maximum reach of 8. Now, as you can imagine, as I was saying earlier, small streets are going to have a small reach, whereas major highways are going to be part of the shortest path between two very large distances, and thus will have a much larger reach. So you can use this to prune nodes when you're trying to find your shortest path. So, if you imagine a bidirectional search, then you know that nodes with a small reach, you're either going to encounter immediately, and they could be part of your shortest path, or they couldn't possibly be part of your shortest path. So you can think of this like the small streets that you'll take at the beginning of your drive to get onto the highway. These are possible things that you might put in your shortest path. But when you're in the middle of your drive, say you're 100 miles into your drive, you're not going to go off the highway to get onto some small street with a reach of, say, 4, so that it just wouldn't be part of the shortest path. With reach, you know that these small reach nodes you'll either encounter immediately and they can be part of your shortest path, or once you're well into your drive, it's impossible that they'll be part of your shortest path. So that's how you'll prune them.
Over the course of this video, we have talked about modifications to several algorithms based on the baseline of Dijkstras, designed to use heuristic functions to get you something very close to the true shortest path quickly. They are loosely based off of the fact that, because of the makeup of transportation networks all over the world, you can divide up edges into roughly two categories, small roads and big roads. So in theory, you should be able to make a small local shortest path search to get from your initial location to the nearest highway network, and then use a shortest path calculation on just the edges in the highway network with a much smaller number of edges before you exit a final local network shortest path search again. In practice, this actually works quite well and is the reason that you can calculate a route from, say, Ann Arbor to Tampa in under a second. The route that Google Maps will show you is not technically mathematically guaranteed to be the shortest path due to the use of these heuristic functions, though in most senses it is very good and practical. However, a recent paper from Peter Sanders and Dominic Schultz claims to be able to exploit highway hierarchies to derive the true exact shortest path for large road graphs in about 8 milliseconds. That is about 2,000 times faster than the current best Dijkstra's implementations, only by using a few hours of pre-processing time in linear space. They prove this by formally defining which edges are sorted into the two classes that we talked about before, local search edges and highway network edges. We can define a local search edge to be an edge within the H closest nodes from your starting position S. So say in this graph we wanted to start in Pleasanton, and we started right in the heart of the city, and our tuning parameter was something like 12. If we started at this intersection here, basically the 12 closest hops would be included in that initial local network. And the highway network can then conversely be defined as an edge is a highway edge if nodes that make it up S and T, U and V, is on the shortest path from S to T. V is not within H closest nodes from S, and U is not within the H closest nodes from T. So once we define that formally, we can move forward with some mathematical proofs as to why this will in fact give you the exact shortest path. Now, if we were to look at this graph, we see that it'd probably take more than 12 hops to even get to a highway. And that's where this notion of highway hierarchy comes in. So at this point, the highway network still contains basically all the nodes from the original network. However, we can prune it significantly. We can get rid of isolated nodes. Trees attached to a biconnected component can only be traversed at the beginning and end of the path. So once we enforce that parameter, we can get rid of a lot of these sort of side sprouts off of the highway. We can iteratively continue on this definition so that we sort of form a super highway network, as it's coined in the paper, which basically has multiple levels of highway networks. And that's where the term highway hierarchy comes from. So the idea is that in Dijkstras, you're essentially expanding out equally or in a circle around you. Whereas in this particular implementation of the algorithm, you would pre-calculate which edges classify as a highway edge, and then from there, only use those in the highway calculation of the shortest path, and a much smaller number of nodes needed for the two local searches at the start and end of your route. So if we were to simulate a Dijkstra's calculation, we can do that as such. And as you see, the red line represents a straight shot from your source to your destination. And this is Dijkstra. So if we zoom in, we can see that it's exploring all these side streets within this side city on the route. We've started around here and we're trying to go over here. Of course, a real shortest path would not need to explore all these highway edges. So the idea is, if we were to limit this to a certain number of hops to get on the highway, it could do that calculation, it would be done by now. And then they could make use of just this very limited number of edges highway network to pick up these highways to get you in the vicinity of another possible local search. So instead of just exploring just an exponentially larger amount of edges, we would already be on the highway here, probably already be in our final destination, and we could be concluding with that local search there. If we did this bidirectionally, it would for sure be done by this point. So that's a little bit about highway hierarchies. Really, when it comes to optimizing shortest path calculations, it's all about determining ahead of time which edges cannot possibly be included in your final path. If you do this, you can what's called prune them, basically eliminate them from further calculations, and have a huge optimization as a result. And that concludes our deep dive into strategies on how to solve the shortest path problem. Some key takeaways that we have highlighted today is that there exists a trade-off with different sort of algorithms that can solve this problem between pre-processing space and time and query execution time. So what that means is that some algorithms do not require any work to be done up front, but to calculate a shortest path between two random nodes may take a large amount of time to run that calculation in real time. Whereas others, there's a lot of work that can be done up front to build some sort of data structure that embeds information about a graph so that when you go to look for a random shortest path between two different nodes, that calculation can be done much, much quicker. In today's world, there's a lot of mobile apps that seek to provide information almost instantaneously to a user. For this to be able to happen, there must be some sort of data structure on the back end to assist the algorithm in providing that correct shortest path in a quicker amount of time. Hope you enjoyed the video today, and I hope you join us next time. Thank you.